Alright, what is up my homies? Welcome to BrainMelt University. Today we've got a value-packed video for you. Today we're going to be discussing how to build a computer network. Every computer network starts at a conceptual phase. You have to plan out how you're going to design a network before you actually just start throwing equipment in and hoping that it works properly. The better a network is planned, the more likely it is to be scalable, secure, and efficient. In this video, we're going to be talking about basic design features and how you want to go about designing your network based off the size of the organization, plans for future growth, and the amount of money that you have available to put into this network design. As always, if you find this video helpful, please feel free to like, subscribe, share with your friends, and hit the notification bell so you can see every time we upload a new video. The first thing we need to take into account when we're designing a network is, number one, how much money are we going to have available for this network design? If you're trying to design a network that's going to cost hundreds of thousands of dollars to implement, but you're trying to pitch this idea to a small family-owned business that's like 5 employees, you're probably not going to do very well. When we're discussing computer network design, we need to match the capabilities of the network with the needs of the organization, and we need to balance efficiency and cost. Our greatest barrier to computer network efficiency usually comes down to the amount of resources that we have available to us. There are a lot of really neat protocols and features with modern computer networks that can make our lives way easier and can really improve the efficiency of a network. But a lot of these protocols are proprietary and only really available with large enterprise level devices. This can be problematic if you're dealing with a small or medium-sized organization that can't afford this more expensive enterprise networking equipment. Some equipment is very good at an effective rate, but you generally are going to have to sacrifice some sort of capability in order to get a lower price tag. After we've looked at our operating budget, we need to look at the size of the organization and their scalability needs. If we're talking about a small company, being a company that has fewer than a dozen employees who actually need a computer to do their job, you're probably going to be able to get away with a fairly basic network. You can usually get away with a peer-to-peer network where there is no server, everyone has the same level of privilege. This is also sometimes referred to as a work group network. And you can usually get away with very few pieces of equipment, meaning you don't have to go with a structured hierarchical network design. However, when we're working with medium to large size companies, these can be organizations that have dozens to hundreds or even thousands of employees who need a computer to do their job. You're going to want to go with something hierarchical, because the more hierarchy a network has, the more you can segregate, separate, and create efficiencies in your network. Network segmentation also can allow us to make a network much more efficient by allowing direct communication with individuals who are in the same work group and indirect communication with individuals who are in different work groups. Your human resources department is probably going to be doing a lot of communication between the other individuals in the human resources department, but probably very little communication with, say, the customer service department or research and development at a specific firm. If you've segmented out all of these different departments, then your switches can be much more efficient by directly forwarding the information from one individual to another within that work group, instead of having to send that information all the way up to a router and then send that somewhere else. This creates network efficiency, and also by limiting the number of people who have access to these internal departments, we're also exercising network segmentation for a security reason. Hierarchical network design is nothing new, and while most vendors make the same recommendations, they can use slightly different terminology. At any given organization, you're likely going to have something called a main distribution frame, an MDF. The MDF is usually also your entrance facility. This is where your WAN connections and internet service provider connections enter your organization's campus or main building. Your MDF is the center of your network. This is usually where your external facing firewalls, your demilitarized zone, your internal facing firewalls, your routers, and your core switches all reside. The core layer of any LAN design is the center of your network. This is where all other switches connect to eventually in order to get to the internet or to reach other network segments. The core layer's main focus is to provide extremely high throughputs. If we're dealing with a company that has hundreds of employees, Your core switch needs to be capable of processing tens, if not hundreds of gigabits of data per second. Core switches are generally very large, very heavy, and very expensive. The more capabilities that a core switch has, the more likely you are to have to pay more money for it. Core switches usually end up starting in the $40,000 to $50,000 range and can run all the way up to several $100,000. A core switch is extremely powerful, but because our number one priority is high data throughput, we want to avoid certain sorts of exercises that are going to reduce the efficiency of a switch. The more computations or decisions that a switch has to make for any given frame or packet, the less efficient it's going to be. There's going to be more latency in that communication stream. This is why with a hierarchical network design, we also want to throw in a second layer of switches below that. This is referred to as the aggregation layer or the distribution layer, depending on whose textbook you're reading or whose class you're taking. My primary background is in Cisco networking, and Cisco usually refers to this layer as the distribution layer, so that's the term I'll be using, but aggregation and distribution both refer to the same thing. Just an FYI. The distribution layer is where you want to be performing filtering decisions. So if you're dealing with an access control list, this is a list of all of the different hosts or networks that are permitted to perform certain communication on a network. If you're limiting which computer systems have access to, say, the internet, for instance, then your access control list would be placed on the switches that reside in your distribution layer. All of your distribution switches should be connecting back to your core switches. Think of a small campus where you have 4 3-story buildings. One is the first building that this organization ever had, the other 3 were added later, and the one in the middle is your headquarters building. It's also where your MDF is, and it's also where your entrance facility is. Your core switches are going to reside in your headquarters building, but then each building is also going to have its own distribution switches. These distribution switches will distribute this information out to their respective buildings, and they'll also be filtering traffic. So if one building is for the customer service people, one building is for research and development, one building is for someone else, then each of these buildings is going to have different filtering decisions based off who is working there and what they actually require in order to do their jobs. Your distribution switches are not only in charge of filtering, but also disseminating information out to each individual building. Each of these individual buildings is going to have their own data center or wiring closet that resembles the main distribution frame in the headquarters building. They're just going to be smaller in scale because instead of having to control the entire campus, they're only having to control a single building. These IDFs, intermediate distribution frames, are where your distribution switches reside. The distribution layer is going to be pretty important when it comes to disseminating this information out, but these switches aren't going to have the port density to provide enough network connections to the entire building. This is why we add in a third layer of switches called the access layer. The access layer's primary concern is actually providing end users with access to the network. Each of those IDFs is not only going to have their distribution switch that controls the entire building, but they're also going to have access switches that control every floor or every section of that particular building. This way you have enough port density provided by the access switches that every employee gets a network connection, or at the very least we have enough connections to supply wireless access points to provide wireless connection throughout the building. You can also have a floor-by-floor cable cabinet, which might provide a network connection to each floor based off of the cable cabinet's connection. This is also nicer because it means fewer cables that have to be run to each individual floor. So your IDF may or may not contain your access layer. The more efficient way of running your cables is to actually have some sort of smaller cabinet, usually it's about 3 feet deep, mounted on each floor that is able to provide the network connections, so that instead of having to run dozens or hundreds of cables down through the walls of the building down to the first floor, you can instead just run all of your cables from each wall jack to a respective switch on that same floor. You only have to run the uplinks from those access switches down to your IDF in each building. This is a really efficient network design. It allows you to separate out your switches based off of their capabilities and needs. You can usually get away with purchasing rather cheap and affordable switches for your access layer You can go with some sort of middling ground for your distribution layer, and then you can buy one super powered core switch in order to control this network. If you're a smaller organization, then you're probably not going to be able to afford a $100,000 core switch and several $20,000 to $30,000 distribution switches, in addition to all of your $5,000 to $10,000 access switches you have to buy. And so this is one reason why smaller networks normally can get away with what's called a collapsed core architecture. A collapsed core architecture is where you get rid of the distribution layer entirely. This does mean that your core switch is now being required to do the filtering decisions normally handled by distribution switches, and that is going to reduce the overall speed and efficiency of your network. But if your company just does not have the money available to deploy a full 3-tier architecture, then a 2-tier is probably going to be better for you. You do also have to make sure, if you are going to deploy this, that your core switch does have the port density to be able to connect to each individual access switch. Now, best practice for network design is that you should be deploying your core and distribution switches in pairs. This way, if either of your core switches or either of your distribution switches for any given building fails, there is a secondary switch that's capable of taking over. This also allows you to load balance your network in the meantime to allow both of your switches to be performing tasks, which reduces the latency and increases the efficiency of your network, as well as the overall throughput available to your access switches. This allows your network to be highly fault tolerant as well as highly available. You see this term redundancy, high availability, and fault tolerance mentioned a lot when it comes to servers, but the same is true when it comes to networks. If a building has 2 distribution switches and every access switch has a connection to each of those distribution switches, if one loses power for whatever reason or suffers a major fault or hardware failure, the other one can still do the job. Yes, your building is now operating at half of the possible bandwidth or throughput that it did before, but none of your employees or members of your organization are going to completely lose their ability to exchange data and do their jobs. And the same is true for your core layer. If one of your core switches goes down, your second one can still pick up and do all of the forwarding that requires high-speed calculations. This is extremely expensive when you consider that a decent core switch is going to run you $50,000 to $100,000, and a good core switch could cost you upwards of $200,000 to $300,000. And your distribution switches are usually going to be a $30,000 to $50,000 distribution switch as well. But if your company can afford it, this is a very good way to build your network out. It's extremely fault tolerant, it provides lots of redundancy, which is not a bad thing when it comes to networking or IT in general. Redundancy is good if your company can afford it, and it also provides high availability whenever people need it. Now, when you're deploying all of your devices, especially if you're going in pairs like it's recommended, so you have 2 core switches, each building is going to have 2 distribution switches, and then you have all of the necessary access switches, this could create a lot of problems when it comes to the complexity of your network. The difference of having to manage 1 core switch and 4 distribution switches versus controlling 2 core switches and 8 distribution switches is pretty massive, especially if you look at how complex the configurations on these get due to their port density and their extra capabilities. This is why there is a number of switch features, capabilities, and protocols that allow us to simplify our network configuration. Most of this comes down to tricking multiple switches into thinking they are a single switch. One of the most common of these is called switch stacking. The concept of switch stacking is if you have a pair of stackable switches, if you connect both of these switches together, then they can be configured to believe they are one and the same. Both of the switches will share a single configuration file. Both of them will have kind of a backend that communicates between the cables that you use, and both of them will, for all intents and purposes, believe they are a single switch. This can be really nice if you have, say, 4 or 5 access switches on every single floor of a 12-floor building, for instance. If you're using switch stacks, then every single floor can have its own switch stack, and instead of having to manage 48 individual switches, you're now only having to manage 12 logical switch stacks. Stacking is awesome when it comes to access switches, but most of your distribution and core switches don't have the ability to be stacked, but they do have the next best thing, and this is some form of aggregation. Now, you might see terms like chassis aggregation. You might also see references to something called a virtual chassis, or you might see something called virtual switch service, VSS. All of these are for the most part the same idea, where you're convincing two devices to work logically as a single switch. Now, these concepts, chassis aggregation, virtual chassis, or VSS, are not the same as switch stacking. They do operate on a lot of the same principles, simplifying your devices, making them work together, and making all of the other devices on your network think that they're communicating to one device when they're really talking to two, but they do operate on different principles. One of the major principles that these operate on is switch stacking, as far as Cisco is concerned, typically requires a dedicated cable. Switch stacking usually requires a dedicated interface on a device. This might require a special proprietary cable, such as with Cisco's Smart Stack or Stackwise cabling that they use for switch stacks, or they might just use a standard RJ45 or SFP port in order to allow you to connect a standardized cable together. But these are dedicated interfaces on your device, and they will co-opt the computing resources, CPU, RAM, etc., of each individual device to make them believe that they are one and the same. Chassis aggregation is different, where you're convincing the rest of the network that two devices are one, but the two devices are really just coordinating with each other. This is again extremely powerful because both devices will basically attempt to work together, but they still maintain their own configurations. They still maintain control of their own CPU and RAM, but the rest of the network logically sees this as a single device. This way, for all intents and purposes, if you're deploying your distribution switches in pairs, if you're using something like VSS, virtual chassis, etc., all of the access switches that connect to those distribution switches will think they're communicating with a single device, but the two switches are basically just coordinating their exchange of information. If one of those devices goes down, then the network doesn't really recognize that something bad has happened other than their bandwidth has just been cut in half. You as a technician should, however, have some sort of alerting system available to let you know that one of these switches has failed. These capabilities, stacking, virtual chassis, VSS, all of that fun stuff, does come together to make your life a lot simpler, especially if you're working with a company that has the resources to actually construct a network as recommended. However, if you're working with a smaller company, you're going to have to make some sort of budgetary cuts, and usually this involves deploying your distribution switches and core switches as a single entity. This does create a single point of failure, but the organization does have to eventually make a judgment call. Do I want to get rid of single points of failure, or do I want to throw an extra $500,000 at a small campus LAN in order to get rid of that single point of failure possibility? These sorts of network concerns are definitely things that you want to consider as you are designing your first networks. These are also things that you'll want to know as you're moving forward in your computer networking or IT journey, because the more you understand how computer networks are deployed, then the more you are going to be able to do your job, whether you're working in cybersecurity and just need to know how your devices are oriented in your network, or if you're just a general help desk technician and you need to be able to understand how your network is built at your company. So if you're working with a customer who's having network connectivity issues, you know the proper questions to ask the computer networking team in order to help troubleshoot that problem. And with that, I think we're ready to wrap up. If you have any questions, comments, or concerns, please feel free to drop them in the comments below, and I'll see you all here next time at Brainmelt University. Stay safe and have a good one.